So in the last class we saw Newton's second law summarized as net force is equal to ma, and then we also saw the different kind of forces, weight, normal reaction, tension, and so on, right? So what is tension? It's a force that acts in a material because of stretching. Okay, so when you try to stretch a material, the atoms will get pulled in all directions, and that will cause them to come back or attempt to come back, and that causes tension in the material. So in a string you can have tension, cables, tension. Okay, so we will be applying that concept later. Normal reaction is a force, is a contact force from the surface onto the object, and it is always perpendicular to the surface. It's always perpendicular to the surface. And now we have done with chapter 4. Let's go to chapter 5. Are you okay with chapter 4? No?
When will the test be?
Oh, next week. Yeah.
Is it online or written?
I'll decide. But are you okay with it?
Yes.
Shall we go to chapter 5 then?
Sure.
Yes.
How can you say that? There are lots of things that you need to really understand and do. Newton's second law. Second law, you've just done net force equal to ma. That's not the end of it. You have to work through a lot of problems, and each and every problem will teach you something new. And it'll, so once you put all those ideas together, you should be able to tackle problems using the second law. Of course, it's not only the second law. You have to keep an eye on all the laws, okay, and apply it accordingly. So second law, a simple example of a second law is this. If I have an object of mass 10 kilograms, and if how many forces are acting on that object if it is sitting on the floor? 2. Which are the 2? Chris, which forces are acting on this object right now?
The contact force, which is friction, and acceleration due to gravity.
Say it again. One is called the
Weight.
weight. Don't say acceleration due to gravity. How much is his weight? 10 kilograms is weight. What's the weight? 98 newtons. Yeah, when I ask you for weight, weight is a force, you have to say the number. Now it's a 10 kilogram object, obviously 10 times 9.8 is going to be the weight, which is 98 newtons. Okay? So that is 98 newtons. What is the other force acting on it? On the object. The contact force, which is what we call as the normal reaction, and that is normal reaction. Do you know how much it is? 98?
It's not the
Anyone? How much is that force? 98? What's your justification for that? You can't just blindly say something.
It's not flying, balanced.
Say it again?
It's not floating.
It is not floating, nor digging into the ground. So what law are you applying there?
The first.
First or the third?
First.
The first law. You can't apply the third law because these two are not pairs. Those two are not pairs. We saw that in detail. Those are not pairs. They are different kinds of forces. They cannot be pairs. So Newton's first law says what? When the net force is 0, the object will stay in the same state of motion. Right now it is not flying upward, as you said, or it's not digging into the ground. So these two forces, the net force should be 0. When the net force is 0, there is another word for it. It's called equilibrium. You can write it down. E-Q-U-I-L-I-B-R-I-U-M. E-Q-U-I-L-I-B-R-I-U-M. That's equilibrium. So when an object is in equilibrium, what do you know about the net force?
0.
When the net force is 0, what can happen to the object?
Constant.
It can be either at rest or
Constant velocity.
constant velocity. Okay, keep that in mind. So we used the first law and we decided, all right, so this is equal to 98 newtons. Now, if I say that someone is pulling this object here with 100 newtons, and then someone else is pulling this object backward at 30 newtons, what is the net force acting on this object? 70 newtons. So what will happen to the object when there is a net force? It will? What law? Second law. So the net force is equal to ma. See, the equation is a very simple thing, but you need to apply it in the right manner. Okay, so net force is ma. So what is the net force here you said? 70 is equal to, what is the mass? 10. A, what is A? 7 meters per second square. So it's going to accelerate in this direction with 7 meters per second square due to the net force. There are so many forces acting on it, but the net force is only 70. Which way? That way. Make sense? Okay. Another problem, let's say if you have, again, a 10 kilogram object, and if I say that, all right, you're looking at the object from above, so imagine the object is on the floor. Imagine the object is sitting on the floor, and you're looking at the object from above. So someone is pulling the object this way with some force, someone is pulling the object this way with some force, and someone is pulling the object this way with some other force. Of course, the angle is given to you. And someone is pulling this object this way. So finally, which way will this object go? What do you do? If I'm going to ask you, all right, this mass of 10 kilograms is being pulled in this manner, what's its acceleration? What is your procedure? We're not going to do problems straight away, but what is your procedure? What will you do in this scenario? Yes?
Could do what we did with like the north, south, east, and west problems and split into vertical and horizontal.
So you resolve it and put it horizontal and vertical, and then split off all of these, and then get the components, finally find the what? Resultant force. And once you find the resultant force, well, the resultant force must be in a certain direction. So if the resultant force is that way, at such an angle, then that means you can find the acceleration also will be in the same direction, right? So you can just take the resultant force and divide by the mass, you get the acceleration. Yes? Yeah, we're not doing it, but you know the procedure, right? So if you have more than two forces or something like that acting on an object, you just have to find the net force. Now, sometimes you may have to use a method of resolving to get there, and sometimes it can be very easy, like in the previous problem. In the previous problem, it was very easy because it was going in that direction, so we just used it. But here we don't know which way it's going to go, so we just applied the method of resolving, got the resultant, just the same way as you found the resultant of displacements and all that. And then after that, use it. Because forces are vector quantities, you can use this way. Get it? Objects on an incline. Objects on an inclined surface. So let's say an object is sitting here. The mass of the object is m. The mass of the object is m, and it is sitting there.
Force, the gravitational force.
All right, one by one. So first is the gravitational force. Where does it act?
From the center.
On the center. Okay, here goes the gravitational force. How much is that?
Mass times net.
Mg. See, it's another way of writing weight. Weight is W, right? We can always write mg, because that's what it is. Mg is the weight.
And then the normal force.
And then the normal force is acting which way?
Up or perpendicular to the incline.
Right, that is a normal force.
And then friction.
And then there will be friction acting in this direction, holding it in place, right? So if I'm looking at this object here, sitting on an inclined surface, and it's not moving down, obviously there is friction. Which way is friction? That way. Okay?
Where will that arrow be coming from?
Oh, it's from the ground, so just draw a line right on the surface. It's not on the center of gravity. It's on the contact surface. All right? So here we have the two for, like, let's say friction is not there. Ignore the friction part of it right now. We'll bring in friction later on, and then after that, when you're solving problems, friction should be thought of also as a major force. and we'll discuss about friction later. But right now, if the friction is not there, there are only two forces acting on it. One is this and one is this. Can it be in equilibrium? Can two forces like this keep an object in equilibrium? In other words, can two forces like this cancel off their effects? Yes? Some of you are saying yes, some of you are saying no. Let's say, for example, someone tried to rope on me like this, and Kian is pulling me this way with a force, and someone is pulling me that way with a force. Can they cancel the effects on me?
No.
Not at all. Not at all. Because those two forces have components acting on me which is pushing me this way. So I'll end up going that way. Alright? So this thing is going to go which way? Down the incline. That's what happens, right? You can see the thing is going down the incline. Okay? Why is it going down the incline? Because the net force acting on it is this way. We know the direction already. We already know the direction because you saw it going down.
What's the third law paired to the normal reaction?
The block pushing this surface down. The third law pair for this is the block pushing the surface down. We don't mark it here. You know why? Huh? That's a good question. Why don't we mark the force that this is applying on the inclined surface? That's because when you draw a force diagram, so what is a force diagram? It's a diagram representing or showing all the forces acting on the object and not by the object. You get it? The forces acting on the object is our concern. That's it. A force diagram is a diagram is a diagram that shows all the forces acting on that object and not by the object. When I'm standing like this, how many forces are acting on me? Not by me. How many forces are acting on me? One is the weight down. The other one is the normal reaction from the floor, right? Those are the only two forces acting on me. Now, what are the forces acted on by me? Huh? By me. I'm pushing the ground down, right? That's one force. Then
You're pulling the earth up.
I'm pulling the earth up with 804 newtons. We don't have to bring all those things and draw it because we are not concerned about those forces. What I am concerned of is what is acting on me and not what I am doing. My performance will be based on how I am influenced by others, not how I am influencing others. Makes sense? My performance, my development will be based on how I am influenced by others. Well, some people who I don't even know may be motivated by me. That is not going to affect me. So a force diagram is going to be a diagram that is representing all the forces acting on the object and not by the object. You can write it down somewhere. So why am I not drawing the force like this, showing that this is pushing the surface down? Because the surface is not our concern. Our concern is this object. What's happening to the object? That's our concern. So we show all the forces acting on the object and not by the object. All right. And we know it's going down this way. So how do you find a resultant? Even if it's two forces, how do you find the resultant? We just do the same resolving technique. So here we go. Now this, see, we are going to tackle this in a little way, in a different manner because it's going to go this way, right? Mm-hmm. Since it's going this way, I'm going to consider this to be my x-axis. And this is my y-axis. So you have to tilt your head like that, and then you can understand. So this is like your horizontal and this is like your vertical. Make sense? So these are the two things. Now this angle over here is called the angle of the incline. So what we now have to do is we have to split this weight into two components. We need to split the weight into two components. This weight has two components. One is this way, and the other is this one. So the weight has two components. We need to be able to split this into two components. So if this angle is theta, what is this angle here? Bring your geometry out. If this angle is theta, what is this angle here?
I guess.
90 minus theta. How do you get it? Yeah, because if I drop this down, it's a 90 degree here, so it's a right angle triangle. So it's a 90 degree here, and this is theta. So this should be 90 minus theta. Now my second question, if this is 90 minus theta, what is this angle here? How much? The theta? It is. How do you get that? How do you know that this is theta? It is. Which one is complementary? These two? That's right. So the total angle here is 90, but this side is 90 minus theta. So this must be 90 minus theta. 90 minus theta, which is 90 minus theta plus theta. Right? So the answer is just theta. So the angle here is theta. Confirmed. What is this component? If you know that this angle is theta, this is mg, we're going to resolve the mg into two components. Tell me what is this component? Is it the sine component or cosine component?
Oh, it's the cosine.
Why?
Because it's adjacent.
Because it's adjacent. This is touching this angle. So this is mg cosine theta. What is this then? What is this, Sam? If this angle, if this one is mg cosine theta, what is that part?
It's sine.
Mg sine theta. So now that we have split this into two components, forget about this mg. You can just forget about it because we already split it up, right? We can just ignore this mg now from the picture. Just forget about the term. Now how many forces are appearing to be acting on this? 3 forces. See this one here, you see this one, and you see this one. Now what do you know about these two? They are equal. So what is the normal reaction here?
mg cosine theta.
What makes you conclude that?
The net force is 0.
Net force 0, first law, right? The first law tells you that this object is neither going upward nor sinking into the incline, and therefore the net force must be 0, right? And therefore these two forces must be balanced. So out of the 3 forces, these two are cancelling off. So what's the only force left? That will be the resultant force. So the resultant force of this is just this.
Did you get that mg's on from doing the resultant from down
Yeah,
there? And
because yeah, that is the same thing as mg sine theta. I'm just drawing it a different place. That's it. Because mg is acting here, so even though it is this component, it's acting at this point. Okay. So what is the resultant force acting on the block? Mg sine theta. The only force acting on it is mg sine theta, and therefore net force is equal to ma. Apply that. What is the net force here? Mg sine theta should be equal to ma. So what is the acceleration? What's the acceleration of that object sitting on that incline, on a frictionless incline? G sine theta. So acceleration is G sine theta. So what is the acceleration down the incline? It's G sine theta. Okay. Like for example, you have a road that is downward sloped like this. If you have a road that is downward sloped, you sit on your bicycle here and just take off. You don't have. Do you have to really pedal? No. The bicycle goes by itself. What's the acceleration? G sine theta. So if a question is asked, what takes the bicycle by itself? What takes the bicycle down on its own? What is the thing that is taking it down? And many students say the weight of the bicycle, gravity. Gravity is downward though. It's only a component of the gravity. What component of gravity? The sine component of gravity, right? You understand? So it's just, it's mg sine theta which is taking it this way with an acceleration of g sine theta. But is that acceleration going to be always g sine theta? Not necessarily, because as the bicycle starts speeding up, then air resistance and other things start coming up, then it will it will reduce your acceleration. But initially what is taking it down is the g sine theta. Acceleration is g sine theta. Get it? That is, of course, there is no friction involved. Without friction, the downward force is that. Now what about the normal reaction? The normal reaction is mg cosine theta, generally. So when something is sitting on it here, when this thing is sitting on here, what is the normal force acting on this right now? It is mg cosine theta. Watch this. Mg cosine theta, right now, it is mg cosine theta. Now if I reduce this angle to 0, what's the normal force now? It's mg cosine 0. What's cosine 0? 1. Cosine 0 is 1, so what's the normal force? Just mg. So on a horizontal surface, such as where I'm standing right now, what is the normal force acting on me? It's equal to my weight. Correct? But is it going to be always the case? No. It's not always the case. So when I tilt it like that, the normal force is less. Now, it's further less. Because now what's happening is it's barely sitting there. Look. Now, it's very little. It's not really sitting on it. What about that 90-degree angle? What is mg cosine 90? What's cosine 90? 0. So, if I release it from here, what is the normal reaction? None. It's not even sitting on it. It's not sitting on it. The normal reaction is nothing. So if you go to theta point and all that, like those, it takes you all the way to the top, and there's almost literally a vertical drop. There's hardly any force with which you're sitting on the roller coaster at that point. You're coming literally down like this, but not for long, but it kind of turns around. Have you been on that? No? Yeah, I've been on that. It's pretty cool. For a moment you just start seeing as if you're falling straight down. Yeah, it really gives you. So that means like you won't be in contact with the roller coaster at all at that point. As soon as you start bending like that. But then very soon it starts tilting, and then it, so the force that is holding you, like normal force, is mg cosine theta, and so the contact force kind of reduces. So if you're on a horizontal road in a car, you're having good contact force. Now if you're actually going downhill like this, you're not having good contact force. And then if you have to apply brakes and stop, that may be hard. Because first of all, the grip is not there. You know what I'm saying? Applying brakes on a horizontal road is far, totally different from applying brakes when the road is going down. You may not be able to stop also because the friction is less. Friction depends on this contact force. Yeah?
So when you're talking about as the slope of the incline, as it gets steeper, the object just basically seems to fall straight down. But can you draw that? Not as much as you're doing that one, but because if I'm thinking about the resultant of the perpendicular to the.
Yep, I'll get you that. I know what he's talking about. So if you're talking about an incline that's going like this, so the object is sitting here. What are the forces acting on it? That's a weight. Okay. Now what are the components of that weight? Now we're looking at the components in these directions. So what component of this is this way? And what component of this is in that direction? You see that? See what happened to the normal force? The normal force is also relatively small, but the downward force is a lot. So the normal force starts reducing. You can see how small it is. Is that what your question is?
So, but how does the resultant come out to be like that green?
Because these two are cancelling off anyway. And so the only thing that is left out is this, which is mg sine theta. The only force that is left behind is this mg sine theta. The other two are always going to be equal to each other.
Okay.
The component of gravity and the normal force are always going to be equal to each other if the object is sitting on the incline.
I was thinking of it as like the resultant of the.
So what takes anything down an incline or is mg sine theta. So if I'm keeping this marker on this meter stick, which is absolutely horizontal, what is the force with which this marker is trying to go this way?
Wait.
No, this way. What is the force with which this marker is attempting to go this way, to the side? 0. Why? Because mg sine? No, 0. 0 here. So mg sine 0. What is sine 0? 0. So there's no attempt to go. Now when that angle becomes even 1 degree or 2 degrees, you can see it starts moving down, right? Because now there's a component of gravity in that direction and it starts working from there. Okay? We will delve into those things as we keep going. You got the main idea here? That these are concepts that you're going to use into multiple problems, and the concept is simple, which is normal force, mg cosine theta. Downward force, down the incline, mg sine theta. So, right. Connected objects. So how do you deal with connected objects? When objects are connected with each other. When objects are connected with each other, like for example, you're driving a car and you've connected a trailer along with your car. So now there are two objects connected together, right? Or if you're driving, if you're thinking of a train, look at all those little compartments, they're all connected together. Those are connected objects. So when you have connected objects, in other words, when you have multiple objects moving, how do you tackle those problems? Simple. The rule is apply Newton's second law to one object at a time. Okay? Treat each object independently. Don't mix the whole thing up. Take one object at a time, apply Newton's second law, and go from there. Okay? That's what you do for connected objects. Now I'll give you some examples. And let's say this is a tabletop. That's a tabletop, and let's say there's no friction. Let's say there's no friction. There's a tabletop and no friction. And on the tabletop, here is a mass of 10 kilograms sitting on it. And then I connect a string to it, and I'm connecting it to what is that? A pulley. So I have a pulley attached to the corner of the table here, and this object is sitting here, and I tie a string, and the string here has a mass of 2 kilograms. Now, do you understand the scenario? So it is a frictionless table. You keep 10 kilograms there, and then with a string attached to a 2 kilogram mass. Now this is connected system. It's a system of connected objects. When you have such problems, first thing is you have to use your brain, use your logic. You have to use your logic. Now, what do you think is going to happen to this block, the whole thing together? Do you think this whole thing is going to scoot this way, or not move at all, or go this way? It's going to move?
Yeah.
Which way?
To the right.
To the right or to the left? To the right. to the left is kind of unimaginable, right? Imagine this block is sitting here and something is pulling from this side and this whole thing starts pulling the guy out from there. No, that is practically not possible. So yeah, you can make mistakes by not using your brains. Some people actually end up saying that this is going this way. Why? Because it's bigger, heavier, you know? Yeah, I mean, like if you don't really think practically into it, then you may make some blunders and then you just go from there. All right, so we know that it's going to go this way. So since you know that it's going to go this way, let's say that, okay, this is going to accelerate like that. Now, since they're connected systems, if this is accelerating with A, what's this one's acceleration? A. It's like you're pulling the trailer with a car. If you're going at some acceleration, the trailer must be having the same acceleration, right? So they're connected systems. So how do you tackle this problem? This is what you do. Take one object at a time. Only one at a time. There are two objects here. So let's take this object. For the time being, just focus on this. Don't worry about that at all. And what do you do first? Force diagram. Mark all the forces acting on this block. Can you do it? Okay, what are the forces? Tell me. Don't worry about this side. How many forces acting on this? How many forces? 2 forces? Or 3? 2? What are the 2? Gravitational force, how much is that? 19.6 newtons. That's a weight. Gravitational force is acting on it downward, which is 19.6. What else is acting on it? The string, what is it? What kind of force? What's the word? Tension. Pulling it up. Yep. There's a tension in the string, which is what is it doing to the 2 kilogram mass? Pulling it up. So now we have 2 forces acting on it. Tension upward, weight downward. And we have logically guessed that it's going to be going downward. Right? Now if your guess is wrong, you'll get some awkward wrong and negative answer. And then you have to rethink the whole problem. You understand? If in case you made a wrong conclusion, which is possible. In this case, it's not possible because it's only 2 objects. But there are situations where you will be wondering, is it going to go this way or that way? Confused? No worries. Take it one way and go on. Very soon you'll discover that is wrong. And then you just start working again the other way. Okay, that's one way of tackling this problem. So since it is accelerating this way, tell me, what do you think is bigger, this or this? The 19.6 is bigger, right? Now, in all these Newton's law problems, it's better not to use sign conventions for down is negative and up. No, completely forget about sign conventions. You always go for this. The greater minus all the weaker ones is the net force, right? So we're going to apply Newton's laws here. Net force is equal to ma. There are only 2 forces acting. One is this, one is this. Which is greater? So the greater minus the smaller is equal to what?
2a.
2a. Yeah, you can't solve it. You just have 2 variables. So all you have to do is just leave it there for the time being. Because you're not solved the whole problem, right? So leave it there. So we have one equation. Now go to this object. Forget about that completely. Go to this object and discuss all the forces acting. What are the forces acting on this object? Gravity acting down. How much? 98 newtons. And what else is acting on it? The normal force. How much is the normal force? 98. You know that. And what else is acting on it? Tension. Acting which way? To the right. So the same string which was pulling this object upward is now pulling this object this way. That's why I said tension does opposite things to the opposite ends. So tension is acting in that direction. Now what is the net force? Net force is equal to ma. What's the net force here? Out of the combining all the 3. Just T. So T is equal to
10a.
Now we have T equal to 10a here. And we have another equation there. What do you do now?
Substitute.
Substitute or eliminate or do whatever you want. So 19.6 minus 10a is equal to 2a. So that brings you 19.6 is equal to 12a. So that will help you to solve for a. How much is a? 1.63 meters per second square. So we solve for the acceleration. See, we understand that it is accelerating that way. It is accelerating that way. So since we got a positive answer, our guesswork was right. It's a positive answer. Now how do you find the tension? Substitute that A into any of the equations. Now here is fine. T is equal to 10 times 1.63. So how much is the tension? 16.3 newtons. That means this tension is actually going to be 16.3 newtons. And this tension here is 16.3 newtons. Now look at this. 19.6 pulling it down, 16.3 pulling it up, and that's why it is accelerating. If it was not accelerating, what do you think about these two forces? If it's not accelerating, it should stay the same. Right? If it is not accelerating, this and this should match up. What do you mean by not accelerating? Either it is not moving or moving down with constant velocity. If it's moving at constant velocity, then these two should be the same. But now it is not moving at constant velocity, it is accelerating. So this is how we solve this problem. So we solve for what is the tension in the string and what is the acceleration. Any questions on this? Now you can do one of yourself. Right? Okay. Here's the problem. That's the ceiling. And there is a pulley. And this pulley, there's a string hanging on both sides of the pulley. And there's a mass over here, 7 kilograms. There's a mass on this side, 5 kilograms. And if I release it from rest, if I leave it like that, which way do you think it will move? Clockwise, counterclockwise, or not move at all? Counterclockwise. So you know it's going to accelerate in one way? Go ahead. Solve for tension and acceleration. Find out what is the acceleration and what is the tension. You will get the same answer, 1.63 meters per second square. And the tension will be something like 50 something. Alright? 57 point something.